Hello there, welcome to this video where I'll be presenting the vertical relationship that exists from the cubic function to its first derivative and the second derivative. Okay, now when you look at the cubic function in general format, usually this is how we write it out, and we are going to use the variables and offer general expressions for the first derivative and the second derivative. Okay, so here we go. First derivative will be 3ax squared plus 2bx plus c. Second derivative, which is the derivative of the first derivative, will be 6ax plus 2b. Okay? The exercise in mathematics, and actually a crucial question to ask, is what does the answer mean? In other words, the whole intention in the exercise of mathematics is not to arrive at an answer. It must be that we need to arrive at a meaningful answer that makes sense to the original problem or the original context in which the challenge has been presented in. Okay, so assuming that you have taught, the properties, of the quadratic function and the linear function, as we see that these are the resulting functions from the cubic function here. So we know that is a quadratic function and we know that is a linear function. Okay, so we are now wanting to understand the following. If we equate the second derivative to 0, it means we are finding the point of inflection, right? So the point of inflection, we know that f double prime of x is 0. Now, using this expression, we have 6ax plus 2b is equal to 0. We have 6ax is equal to negative 2b, and x will be negative b over 3a. Okay, so that is in general format the x-coordinate of the point of inflection using the variables that the function has been given in, or the specific numbers that we have from the given function. Okay, now how do we associate this to the first derivative? I'm going to complete the square of this quadratic function and see if it will have any relationship with what. So for the first derivative, the quadratic function at stationary points, we know that the derivative of the cubic function will be equal to 0. So at stationary points, we know that f prime x is equal to 0. Using this expression and substituting 3ax squared plus 2bx plus c is equal to 0. Okay, now let us complete the square and convert the standard format to the turning point format. So let's do that. We factor out the 3a here, x squared plus 2bx over 3a plus c over 3a equal to 0. So we have x squared plus 2bx over 3a. Okay, and I'm going to use different color for that. So it's a half of that, and you square that, so it will be 3a squared minus b over 3a squared in the brackets there. And we have plus c over 3a that remains. Okay, now the first three guys here will give us our square of a binomial, which will be x plus b over 3a squared. Are we seeing the relationship? Yes, we're getting there. And we end up with minus b squared over 9a squared plus c over 3a, okay, is equal to 0. Now if we clean up, multiply out the 3a, we end up with 3a x plus b over 3a squared minus b squared over 3a plus c. obviously you can further simplify that. But the point that I want to talk about here is that now the turning point of our parabola is negative b over 3a, and that will be our y-coordinate, negative b squared over 3a plus c as the y-coordinate. Okay, so we learned that the turning point of the parabola, the quadratic function, is the same as the point of inflection, or the x-coordinate of the point of inflection, of which the solution here represents the x-intercept of the linear function. Okay, so how do we show that vertical relationship in terms of the graphical representation? So suppose this is our frame of reference, or our xy axis, right? I'm going to draw in the cubic function, cubic function, and suppose that is our cubic function, right? The point of inflection is here. What is that? Negative b over 3a. And in terms of our first derivative is our quadratic function. And what did we say? At stationary point, the first derivative is 0. There is the first derivative equal to 0, and somewhere there, the first derivative is also equal to 0. That's why even later in optimization, we ask the students to maximize quantities or minimize quantities, and they have to find the first derivative and equate it to 0. Okay, so what do we know? That will be our x-intercepts of the parabola. Okay, so that will be, suppose, x1, and that will be x2. But what do we know? The turning point will be the expression that we got here, negative b over 3a, and that is exactly what we're going to have. Now looking at the concavity here, it means our a is positive, and this is what we're going to have as our parabola. Okay, and the last thing is the linear function, okay, and that is the expression. A is positive, as we spoke about the concavity, meaning it has a positive gradient, is an increasing function, and this represents the x-intercept, right, where the y-coordinate is 0, and that will be your linear function. Okay. So what have we done? We have shown the vertical relationship. There is your x-intercept of your linear function, there is your point of inflection, and that is your turning point. So that is the vertical relationship that can always be associated with this context and the variables from the original function. And I just want to highlight that this formula is what learners can use in differential calculus when they talk about these situations. Okay, so that is it for this video, and I hope it was helpful. You can also try it with when a is negative and draw a different type of cubic function and see what happens there, and play around with the numbers. So there's a whole process that I wanted to show, and thank you for watching. See you in the next video.